from the worst scenario. And we discussed about it, and we call that as Minimax. As the name suggests, Minimax means minimize the maximum risk. So minimizes maximum risk. So that means I'll call delta star to be minimax if the maximum risk of delta star, which is supremum over r theta delta star, is the smallest among all the estimators. So this is same as, it is smallest, that means infimum delta belonging to D, supremum theta belonging to theta, r delta theta for any other estimated data. So this is called min-max estimator. Then we talked about posterior distribution. So note that to begin with, the only thing available to the statistician was his personal belief, which was in terms of a prior distribution. Now after the data has been taken, he has more information about the unknown state of nature. So prior distribution was the information about theta, which was based on statistician's belief from the past experience. After the data has been taken, there is additional information about the unknown state of nature. So what statistician does is, he tries to update his prior information in the light of the data he has. So that means, in certain sense, he is talking about the conditional distribution of the state of nature, which is S, given that data has been observed. So posterior distribution is nothing but distribution of S given, suppose data has been observed as small x. So one can talk about Q of S given x, S is given to be theta, and x is fixed at small x. I know this is same as joint divided by marginal. Joint is, so I can write down this as Q of Sx theta x divided by Q of xx, which is marginal of x. What is the Q of Sx? This can be written further in terms of a conditional, and so this can be written as Q of x given S, x given theta. Then Fs theta, which is nothing but d pi theta, divided by Qxx, which is basically integral of the whole numerator. So what is that? Q of x given as theta is the distribution of x when state of nature is known. So it is the usual PDF, the frequentist PDF which you have, which is nothing but f of theta x d pi theta divided by marginal of x. This was a joint, so marginal is that this integrate out theta. So this is the posterior distribution, which is nothing but an updated prior information in the light of the data which you have obtained. Then we talked about Bayes action. So in certain sense, what you know is all the information about theta, one source of information was the prior distribution, one was the data. Now everything has been combined, and everything has been squeezed into the posterior distribution. So in certain sense, now the only thing which should matter is the posterior distribution. So Bayes action is Ax that minimizes expected value of S given x equal to x So posterior loss. So L theta A given x equal to x. So this is the thing which is called the Bayes xn. Then we saw that Bayes xn is in fact gives me a Bayes estimate. So Bayes estimator is nothing but the one which minimizes the posterior loss. So let us try to see some of the scenarios. What would be the Bayes estimator in such scenarios? So let us consider first example. L theta A is nothing but, let us say, A minus psi theta whole square. So let me try to minimize let me call this as tau of A, which is nothing but posterior loss. That is what I have to minimize, which is nothing but expected value of S given x equal to x of A minus psi. In place of S, now you have in place of theta, you have a S, because theta is the realization of S. So this everything is in terms of distribution of realization given the data. And how much is that? That is expected value A square, expected value of S given x equal to x of, so that is just A square minus twice A expected value of S given x equal to x. In fact, there was no need to do all this. So you are trying to minimize this, and you know that the squared error is minimum from which point? When A is the mean. So that means this will be minimized when A is the posterior mean of psi s. So Bayes xn Ax is nothing but expected value of S given x of psi s. As given x means it is a posterior distribution, and you're talking about its expectation of psi s. So that means Bayes xn is nothing but your posterior mean. So what it suggests is that if you have a squared error loss function, then the Bayes estimator is nothing but the posterior mean. And you can see that, in fact, this minimum is unique because it is a quadratic in A square, expected value of S given x equal A square minus 2A, so it is strictly convex function. Double derivative is strictly positive. So that is why the minimum would be unique. So this is also the Bayes estimator. So what it suggests is if you have a squared error loss function, you just take the posterior mean, and that would be your Bayes estimator. And posterior mean is basically the mean with respect to conditional distribution of S given x equal to x. Okay, now let's consider one more. Or two more examples. Suppose L theta A is nothing but A divided by psi theta minus 1 whole square. This kind of a loss function, we saw that arose when we were dealing with the scale families. So this was the form of a scale invariant loss function. So what I have to minimize? I have to minimize psi of A, which is expected value of S given x of a by psi theta minus 1 whole square. So I can expand it. A is a constant, so it is a square expected value of s given x 1 upon psi square theta. This would be psi s because theta is a non-random variable which is denoted by s, psi square s, minus twice a expected value of s given x of 1 upon psi s plus 1. Now you can see that psi double prime a is 2 times expected value of s given x 1 by psi square s, which in most situations would be strictly positive because psi s is equal to 0. This would be 0 only when psi s is 0, only when psi s is infinity. That will never be the case. So what is the Bayes estimator or the Bayes xn, which would also be same as the Bayes estimator? So ax is nothing but where derivative is 0. Derivative is 0 means twice a esx minus 2 is equal to 0. So that means a is same as this divided by this. So this is same as expected value of s given x of 1 upon psi s divided by e of s given x 1 upon psi s whole square. All right, we can consider the third scenario, absolute error loss. Let us say mod of a minus psi theta is called absolute error loss. What I have to minimize over here to get the Bayes estimator? Posterior loss. So psi of a as e of s given x of mod of a minus psi of s. Now we also know that absolute error is minimum when a is same as the mean of psi s. So that means in this case ax is nothing but the median of psi s with respect to distribution of s given x. So which is we call as a posterior median of psi s. So we considered 3 examples. One was the squared error loss. In the squared error loss, we saw that your Bayes estimator is nothing but the posterior mean. The third one was absolute error loss. When the loss is absolute error, your Bayes estimator is nothing but posterior median. When your loss function is of the type a upon psi theta minus 1 whole square, the Bayes estimator is given by this quantity. So a ratio of 2 expectations. So let us take one example where we can specifically find out what are the Bayes estimators. Okay. So suppose x1, x2, xn are IID, Poisson theta. Theta greater than 0 is unknown. Estimate is psi theta, which is theta to the power m for some m not equal to 0. I consider estimation of theta to the power m under two different loss functions. One loss function is the square error. So L1 theta A is same as A minus theta whole square, A minus theta to the power m whole square. The second loss function could be A upon theta to the power m minus 1 whole square. A has to be positive because your estimate is positive, theta is positive. Suppose my prior is theta, which is a continuous variable because theta can take any value greater than 0. So I have to get a prior in terms of some continuous distribution. So let me take prior to be the gamma distribution. So prior distribution Fs theta, which I am taking as theta to the power alpha minus 1 e to the power minus theta by gamma nu gamma alpha nu to the power alpha. Right? So it is a gamma prior. Where alpha greater than 0 and nu greater than 0 are known quantities to you. So from the past belief, one says that normally this theta behaves like a gamma distribution. Now to find what will be the base estimator. Now we have realized that for finding the base estimator, I need to find the posterior distribution, because posterior distribution is the distribution which has all the information about unknown state of nature. So I need to find out Q of theta given x, posterior distribution. If you want to write down so that everything is clear. So it is a distribution of S given x, theta, when S is given as theta. Now, we know that conditional PDF is proportional to the joint. What is the joint? Joint of S and x at theta and x. So this is proportional to f of S x theta x, because in fact it would be joint divided by marginal at x, marginal of x at the point small x. But here x is a fixed quantity, so it would be some constant. So that is why I have put proportional to. Finding that proportionality constant, which of course would depend on what this fixed x is, will not be difficult. But this is same as f of S given x, theta given x, and Fs theta, which is nothing but f theta x into Fs theta. So this is the routine thing which I'll be doing all the time in finding the posterior distribution. So what I get is posterior distribution is nothing but proportional to the frequentist PDF f theta x divided by multiplied by prior PDF. Very simple. And what is that? F theta given x, I know is Poisson theta. X1, x2, xn are IID Poisson theta. So what is f theta x? Product I is equal to 1 to n e to the power minus theta, theta to the power xi by factorial xi. Then Fs theta, which is theta to the power alpha minus 1 e to the power minus theta by nu by gamma alpha nu to the power alpha. Of course, data is given to you. Data is this x. Data is nothing but realization from Poisson theta. So that means your x has to belong to 0, 1, 2. So nth Cartesian product of 0, 1, 2 to n. Okay, now the range here is theta is positive. I can exactly find it out what this should be. So I don't care about constants over here, including x, because x, any factor which has a x is a constant. So I just collect the factors of theta, because they are non-constant. So this is further proportional to, because that proportionality constant I can find out later on, because total integral has to be 1. So proportionality constant one can easily find out. Of course, that proportionality constant is going to depend on what this fixed x is. Okay, so what is this? Note that e to the power minus n theta would come from here. So what does that become? E to the power minus theta e to the power minus n plus 1 by nu theta. All right, and then theta to power summation xi plus alpha minus 1 so this is taken care of factor of theta, this is taken care of factor of theta, this is taken care of, this is factorial xi is a constant depending on xi, I need not bother about that. Gamma alpha is a constant, nu to the power alpha is constant, so this is this. In fact, now I know what would be the constant, because it is of the gamma form, theta to the power beta minus 1 e to the power minus beta theta. So in fact, I can directly write down now what would be my posterior distribution. This is nothing but n plus 1 by nu to power summation xi plus alpha divided by gamma of plus alpha e to power, sorry, e to power minus n plus. So these are proportionality constant, right? Because total integral has to be 1, and I could immediately relate that this is a PDF of a gamma. Once I know the PDF of a gamma, I know what would be the proportionality constant, which is this, and theta to power now under loss L1, I know my base xn would be posterior mean. So under L1 delta pi x, which is same as Ax, is nothing but posterior mean. What is a posterior mean? So what is a posterior, what is the mean of this distribution? Gamma alpha is nothing but alpha divided by beta. So that means summation xi plus alpha divided by n plus 1 by nu. So that is same as summation I is equal to 1 to n. I can now replace here by the random variable xi plus alpha n plus 1 by nu. Now let's see, what we have seen is, in the Poisson case, for example, UMV UE is x bar, which would be the case when alpha is 0 and 1 by nu is 0. But alpha is not 0, because alpha is anything positive, and nu is greater than 0. But in limiting sense, this is same as x bar. This goes to, as alpha goes to 0 and nu goes to infinity, this goes to x bar, which is the UMVE. And UMVE was available to you without any prior information. So let us try to think statistically. What does this say? That this should convey something. It says if alpha goes to 0 and nu goes to infinity, then my Bayes estimator is same as the classical estimator, which is the classical UMV-UE. So let us try to interpret what does alpha going to 0 and nu going to infinity means. My prior was this. Prior was this, what does that mean? That means what is my mean? My mean is nothing but alpha times nu. What is the variance? Alpha times nu square. In fact, what you can do over here is you can further simplify this. Let me try to do that. This is nothing but nu times xi plus nu alpha divided by n nu plus 1. In fact, if nu alpha goes to infinity, this will go to x bar. If nu alpha goes to infinity. Now, nu alpha goes to infinity, that means if the variance goes to infinity and mean goes to infinity in the prior distribution, then this estimator reduces to the classical estimator. So this goes to so if you want, you can keep alpha to be fixed, and you can say that as nu goes to alpha goes to 0 and nu. So you see this and nu times summation xi plus nu times alpha. Sorry, I'll have to. Let us interpret it just from here. Just sorry for messing a little bit up, but let us try to see. Let us try to interpret this itself. It is clear from here that this, as I wrote before, as alpha goes to 0 and nu goes to infinity, this goes to x bar. Now, nu goes to infinity and alpha goes to 0. What does that say in terms of this distribution? Can I interpret that alpha goes to 0, nu goes to infinity in certain sense? No, this suggests that it goes to the usual estimator x bar. So that means I should have an interpretation that as alpha goes to 0, nu goes to infinity, prior distribution is not contributing anything. Or in other words, this prior distribution as alpha goes to 0 and nu goes to infinity amounts to having no prior information at all. So try to interpret that whether alpha going to 0 and nu going to infinity can be treated as having no information at all. So let me go to the next loss function. Before that, let me just check my expression for the Bayes estimator. I had to get a, this is because I had started with estimate as theta to power m. So I had to get a posterior mean of theta to power m. So this is just the estimate of theta, not theta to power m, because I'm just taking the expected value of theta. If I had to estimate theta to power m, I should have taken posterior mean of theta to power m. So this is okay. So this is a posterior mean of theta, and yeah, so which is nothing but, so which is same as this, yeah. So let us look at the loss function L1 theta a. So try to get this interpretation. I have given you a hint that this, in a certain sense, gives an interpretation that, look, if alpha goes to 0 and nu goes to infinity, I am in a situation of a classical scenario where no prior information was available. So the question is, can I interpret alpha going to 0 and nu going to infinity from the prior distribution as if prior distribution is not providing any information to me? Okay,